So, good afternoon everyone. Today I'm presenting my final PhD thesis. The presentation is divided into two main parts and a final brief discussion on the environmental sustainability. I will go first through the need, the objective, and the experimental campaign that we have conducted on the retrofit system. Then we'll talk about my numerical study to assess the impact of the new retrofit system on the seismic vulnerability of a case study building and the effects of considering global and local mechanisms in both the main direction of the case study building. So my work emerged with the NAM project. It's a project that born with the induced seismicity in the northeast part of the Netherlands, and the project aimed at assess the building stock of the Groningen region, which includes around 250,000 buildings, of which the vast majority is unreinforced masonry buildings. So the major earthquakes that we recorded in the area was characterized by a PGA of around 0.1 G, which are usually considered light as unproblematic from the scientific community. However, many claims were raised up by the population because they were imputing some minor structural or even non-structural damage to the seismic activity. So a huge experimental campaign was started at the U Center, focused on measuring structures. Many activities were performed, from full-scale analysis, dynamic shake table test, material characterization test, in-plane quasi-static test, and of course a lot of numerical effort. With the increasing knowledge of this, of the weakness and the lateral behavior of this building, the interest moved also to some retrofit system techniques. So here I'm showing you the last tested full-scale specimen. It was representative of a Dutch URM terrace house, and it emerged during the experimental campaign as one of the most vulnerable configurations that we can find in the area. It is made by cavity wall system, so there is an internal calcium silicate load-bearing leaf and an external leaf of clay with only aesthetical and thermal function, and they are connected to each other by steel ties. As you can see, the building is highly irregular. It presents an irregular distribution of openings that was taken from a real case that you can see on the bottom left. And if you focus on the plan view that I put here on the ground floor and the first floor, you see that in the transversal side of the building are very stiff, transversally with respect to the ground motion, are very stiff because they are solid walls, while in the longitudinal sides of the building we have only two squat walls, which are distributed in different stories, one at the ground and one at the first story, on the first floor. And all the other elements are highly slender. So this is a very irregular case. Here are some more details about the construction. You can see the elevation and the density of steel ties that connects the two leaves. It was taken as a lower bound of the connection that you can find in situ. And here I put also some details about the floors, because the floor system were laid only on the transversal side, while the longitudinal side, the east and west facade, were left unloaded, and especially they were discontinuous in height. And something I forgot to mention is that we have also a flexible second floor. This is the input that we use, the input signal that we use for the experimental test is, of course, representing an induced seismicity, so it has a short significant duration, high frequency content, and is spectrum compatible with the highest hazard of the zone. And on the top right, you can see the scaling of ground motion that we have applied for the incremental shake table test. The reason why applying such a big amount of scaling was to define also during the experimental test the reaching and the overcoming of damage state of the building. So to classify the damage, we use the well-known Grunthal classification that define 5 damage states and corresponding 4 damage limits. And after each run, we a posteriori annotated all the cracks of the building, So a posteriori we could assign at the end of every run the damage state of the building. And to correlate the damage with the response of the building, we use the global drift as the second floor average displacement above the foundation, because we found it as the most appropriate to correlate damage and the response of the building. So going through the experimental results on the bare specimen, you can see that in the S1 there is no structural damage, and interestingly the PGA of this wear motion is comparable with the maximum one that we recorded in situ. So yes, it's possible that this motion can cause some minor damage, but which is not structural. In DS2, we see the activation of a local mechanism, because the second timber floor was sliding on top of the masonry. You can see from the drift profile that concentrated on that story, and also the damage that concentrated at that floor level. In damage stage 3, the situation worsened, and we have a concentration of damage at the first story, while the ground was not showing significant damage. You can appreciate it also, again, from the drift profile. And here I just put a couple of pictures to show you the level, the amount of damage that we reached, because here the north facade was pushed out of plane by the second floor, which was sliding on top of the masonry. So coming to ultimate condition, this is the video of the last performed run. The PGA was 0.39 G, and I'm showing it to you just to let you appreciate the second floor sliding mechanism. If you focus on the attic floor, you can see how the floor moves independently from the house, so it cannot respond globally to the external excitation. And the final conditions are reflecting this behavior. Again, the ground story was not damaged, let's say, while the first story was heavily damaged. You can see also the drift profile, how the displacement demand concentrated at that story. And you can see also the level of damage that we reach on the bottom left of the intersection between the two walls. We had a residual displacement of 3 or 4 centimeters, so a huge one, while we have also partial collapse of masonry on the east facade, while the ground story was not showing any significant damage. So once we define, let's say, the lateral behavior, and we identify the weakness of the most vulnerable configuration, we started from them to conceive a new retrofit system that has to prevent first the development of local mechanism, so improve the masonry to floor connections. It has to promote a global box type behavior, enhancing in-plane and out-of-plane capacity of walls. And we need also to stiffen the second flexible floor. And additionally, some very appreciated, characteristics of the retrofit system are sustainability, low invasiveness, and cost effectiveness. So to comply all these requirements, we decided to start from the material. We decided to choose timber to create a timber-based retrofit structural system, because its high density, strength over density ratio allowed to keep low invasiveness. It is natural and recyclable, so it's sustainable, and it's easy to be installed, so it's supposed to be cost effective. So we look in literature and we found a solution proposed by Javeton and Bizur and others that use vertical timber posts to retrofit masonry elements against out-of-plane loading. And then we found a way to extend it to improve also the in-plane capacity of masonry walls, and to do so we found valuable suggestion on the American Wood Council, especially regarding timber shear walls. The result of it is what you see on the right, is a timber frame that can firmly fixed to bottom RC beam and top RC beam, which are foundation and floor systems. On top of it, an OSB layer is nailed. Going through the mechanical behavior of this system, so from the out-of-plane point of view, we see that the vertical post can be schematized as a pin-pin beam that adds shear resistance and moment resistance to the wall, preventing the collapse, and especially it guarantees the transfer of out-of-plane forces to floors and foundations. And regarding the in-plane behavior, the flexural contribution of the retrofit system is given by the anchor posts, which are fixed to the base or to the top with tie-downs element, and the shear contribution is given by the nail OSB that we designed, again following the American Wood Council prescription. So once conceived the retrofit system, we start testing a component cyclically in plane. We reproduce two identical specimens, one in bare condition and one in retrofitted configuration. This is the bare pier. It presents a slender nail ratio that is in between slender and squat walls. And here is the retrofit that we mounted on the synchron specimen. It's composed by 4 vertical timber posts anchored by tie-downs on top and bottom. And we have 3 lines of nailing of noggin elements to improve the connection between the frame and the masonry, and also to allow the nailing of the OSB panel. So here is the lateral behavior of the bare masonry. You see an initial flexural response, which was followed by a strand degradation and a sliding behavior to conclude with an hybrid one. You see, at ultimate condition, we have a horizontal crack at the top, and we have some toe crushing at the bases. So what happened at around 0.2% of drift is that the horizontal crack at the top was fully developed, so the masonry could not maintain a flexural response and started to slide on top of it. And of course, the strength decreased. We had to stop the experimental test at 0.75% of drift because the masonry was not able anymore to sustain the vertical loads. Moving to the retrofitted specimen, first I have to say that the first cracking drift was not delayed, and this is because the very different characteristics of stiffness between the timber and the masonry. The timber presents a stiffness that is around 10% the one of the masonry, so in order to activate it, you need the masonry to be cracked. So no delay of the first cracking drift. But if you look the maximum shear, we reach it at 0.8% of drift, which corresponds at the failure of the bare masonry. So the system managed to bring the masonry to higher displacement up to the ultimate condition where the masonry failed in diagonal shear because of displacement compatibility with the timber. The timber was still able to go further with displacement, but the masonry was not able anymore. So we had to stop the test, and you can see from the picture the level of toe crushing that we reached, very, very extensive toe crushing. Comparing the responses, you can see that we had a strength increase of around 35% and a displacement increase of around 167%. And the reason why we reached such an increase in displacement capacity is because of the axial load transfer that occurred between the timber and the masonry. Because with the increasing of displacement, the axial load will gradually transfer to the timber, which allowed the masonry to reach such a high displacement compared to the bare one, and even with such an amount of toe crushing at the base. So once defined the mechanical behavior of the retrofit system, we applied it to a full-scale building prototype, which reproduced the last one that we have tested in bare condition. So we retrofitted the longitudinal side, the sides longitudinal to the ground motion, against in-plane and out-of-plane action. So you see timber frames mounted in every pier. And on top of them, we nailed an OSB layer, as you can see on the right. In transversal sides, being already highly resistant to in-plane action, we only provide a retrofit for out-of-plane capacity to keep it light, to allow the to visually see the cracks forming. And so you don't see OSB, you don't see tie-down, and you don't see noggin elements. Here some details about the improvement of connection. With the first floor RC slab, we use passing through bars, while for the second floor, we use steel angles and nails. And on the right, you see the intervention that we applied to stiff the second floor flexible diaphragm. Is just a layer of OSB nailed on top of it that was computed, again, based on the American Wood Council prescription. A separate speech is needed for the gable roof subsystem, because it was recognized as the most vulnerable subsystem of this typology of buildings. So what emerged from the test is that the failure of the subsystem is governed by the gable walls, by the displacement capacity of the gable walls. As you can see, the gables is collapsing while the roof is still standing. So the roof could accommodate higher displacement. So what we decided to retrofit in our building was only the gable walls against out-of-plane loading. What we left in place a system of loose cables in order to simulate an intervention in the roof system during the shake table with increasing of intensity. Here's the testing protocol. It's exactly the same as we applied for the bare building in order to allow a better comparison of results. But you can see from the testing protocol that we reach higher scaling of the ground motion. So going to the experimental results, you see that in DS1 only the gable roof subsystem was suffering any damage, even if it's still non-structural. Interestingly, we are already at intensity level that is 2 times the maximum recorded one. In damage state 2, we have the diffusion of damage at the gables, but we have no damage at the ground story and first story. And you can see it also from the drift profile. In damage state 3, we have again a diffusion of damage in the gable walls, but interestingly, we got cracks at the ground floor of the transversal north and south walls. The walls transversal to the ground motion. So initially we imputed them to out-of-plane action, but we realized that that was the onset of a torsional response of the building. And we demonstrated it with the recorded measurement, because we see that the lateral displacement of these walls was comparable with the cracking displacement of a squat wall that was tested experimentally. So coming to ultimate condition, here again is the video of the last performed run with a PGA of 0.78 G. And I'm showing it to you not only because of the window, but to show you that the building, even at ultimate condition, was maintaining a global behavior, or responding globally to the external excitation. And this can be also seen from the ultimate damage pattern. You see how much damage is accumulated on the transversal walls. So it demonstrated that the building was responding in a torsional manner, and demonstrated also that we managed to use the high resistance of these walls. You can see also the level of damage that we reached in the intersection between east and south facade, because the two facades for displacement compatibility were tend to detach. So we got very high residual displacement and loss of some masonry portion. Here I'm showing you the hysteresis loop at ultimate condition of the two buildings. You can clearly see that the bare building has a response which is highly nonlinear and highly affected by the local mechanism. Indeed, you see also the shear sign inversion for negative displacement, which means that the structure lost static equilibrium during the test. While if you focus on the retrofitted one, you see a global response with the reachment of significantly higher base shear. Some other conclusions can be made by comparing the backbone curves. And you can see that the initial stiffness is comparable, is almost the same, and this is in line with the very different stiffnesses of the timber and the masonry. So at the initial condition, they are pretty the same. And another interesting thing to note is that the damage limit that we define in terms of drift are actually very similar between the bare building and the retrofitted one. But it's also true that the retrofitted one needs almost twice the shaking intensity to reach the same amount of displacement. Some other interesting conclusion can be made correlating the PGA and the damage state that we have defined. I've also inserted here the DS0, which was defined by Tomasetti and others in previous tests. So, considering the maximum recorded event, it's confirmed that it's possible that they cause some minor damage to the buildings, but no structural damage. But if you look at the period if you look at the hazard with 2,500 years of return period, you can see that while the bare building is expected to be in near collapse condition, the retrofitted one is expected to show minor or moderate structural damage. This slide ends the part of the experimental part. I'm now moving to the numerical study I've performed to assess the impact of the retrofit system on a case study building, considering local mechanism and global mechanism, and considering the ground motion acting in both directions of the case study building. So the objective of the study were multiples. First, we want to assess the impact on the retrofit in a building with the real dimension, with the typical dimension that can be found in situ, because in the lab we had to reduce the transversal dimension to fit the shake table. Secondly, this type of study for this type of structure characterized by very different stiffness in the two directions are usually conducted only in the weak direction. So in our case it's the X1. But it's also true that even if the structure in the other direction is highly stiff, we can have some local collapse of the longitudinal facades. And moreover, of course, our results could support practical application for large-scale estimations. So at first, we built our MDOF system. We decided to use the Tremuri program that rely on macro elements and the equivalent Freeman method. And then we found a way to model the contribution of the retrofit system. We basically split the macro element into 6 parts for displacement compatibility, and then we use vertical truss for the timber post and the inclined truss for the OSB. So the vertical post presented an end frame that was calculated in order to return the force displacement relationship of tie-down element. The same thing was performed for the inclined beam that were calculated in order to return the force displacement relationship of the nailed OSB, always following the prescription of the American Wood Council. So moving to the simulation of the experimental test that we have performed, these are the results of the bare building test. As you can see, we got a good match in positive direction, but as expected, a severe underestimation in negative direction, especially from DS3, because of the activation of the local slide. However, you can see how even in DS3, the first floor acceleration are still reliable. Moving to the retrofitted building test simulation, we got a better match because of the more regular response of the building. Up to DL3 is a very good match. In DL4 you can see how the model is not able to capture such a high displacement, and this is because during the experimental test the specimen suffered a very high stiffness decrease because also of the transfer of loading from masonry and timber, so the model could not capture this behavior. Once concluded this calibration, we extended the dimension of transversal walls, and we derived single degrees of freedom based on their response to the testing protocol of the experimental test. So here you see in red the response of the SDOF system, and in gray the MDOF1. In DS1 and DS2, the SDOF system is not able to capture, of course, the dissipation that occurred, and is not able to capture the highly nonlinear behavior. But we can say that from a global point of view, in terms of maximum strength demand and maximum displacement demand, it returned reliable results. The same goes even if it's emphasized by the multi-degrees of freedom system. The single degrees of freedom can return reliable value in terms of maximum strength demand and maximum displacement demand. Again, first floor acceleration and global displacement were reproduced with a good match. Here's the case of the retrofitted building. Again, we obtained better match because the response of the multi-degrees of freedom was more regular. So we got a good match from all point of views: acceleration, hysteresis, and displacement. And here is the case of the ground motion exciting the models in the transversal direction, in the global strong direction. You see that thanks to the high resistance of walls, the the response remained more or less linear, so we got a good match of results between the single degrees of oscillator and the multi-degrees of freedom. Once I've created the SDOF system for all the cases for the two configurations, I ran nonlinear time history analysis using the ground motion database most representative of the area. It was composed by 250 input signals, and the maximum displacement were then post-processed to create the fragility function that I'm showing here, that are only related to the global behavior of the buildings. So you see that for DL1, for DL2, for low level of damage, the timber retrofit is not impacting the vulnerability of the building, and this is in line, again, with the very different stiffness between the two materials. But we see that for high level of damage for DL3 and for DL4, the retrofit has a huge impact. Especially if you consider 2,500 years return period, the probability of having collapse in retrofitted condition is almost nullified. Focusing on the global strong direction, you can see also that the considered hazard is unproblematic from the global point of view. Moving to the local assessment, we perform one-way bending out-of-plane analysis, and to do it for bare condition, we use the model, numerical model developed by Tomasetti and others, which provided the best trilinear relationship to describe the out-of-plane behavior of single leaf and cavity wall system. And then we had to update this relationship to consider also the presence of a vertical post, which is different if the post is in the tension side or in the compression side. And to do so, we calibrated this relationship that I'm showing you based on the out-of-plane quasi-static test performed by Cassol and others. Then to perform local out-of-plane analysis, I've used the original ground motion for all the elements at the base and the filtered acceleration for all the elements at the first floor level. And I performed it separately in X direction and in Y direction. And then to combine local and global damage state, I've assigned consequences to each possible collapse of a masonry element. For instance, any collapse of a squat wall was deemed as in DS5, so it's bring the whole structure to partial collapse or total collapse, while a collapse of a slender element was deemed to bring the whole structure to DS4. So it's heavy damage, but it's not collapse. For each ground motion, the highest between the two is winning, and this is associated to the PGA of the ground motion. So here is the results for bare retrofitted configuration, where I'm comparing it using only global results and using global and local results. So first you see that the Y direction is the most penalized by the consideration of out-of-plane failure. And this is somehow expected because globally it's highly resistant, but we didn't know anything about local mechanism. While in X direction, out-of-plane failures appear to be more influencing the near collapse condition. They are not influencing the DL1, 2, and 3, but they are influencing the vulnerability to DS4, so to near collapse condition. So in order to compare the vulnerability in bare and retrofitted configuration in X and Y direction, I overlap the curve, and on the left you see that for the bare building, even considering out-of-plane failures in Y direction, in X direction it appeared to be more vulnerable. This is fine, but it's also true that the damage limit 4 that we have obtained for the Y direction is very close to the one in X direction. So it suggests also that it is useful to consider out-of-plane failures also in the global strong direction of the building. The same happened for the retrofit case. Then, since I wanted to produce only a unique set of fragility functions that could consider the ground motion in both directions and could consider global damage states and global damage states due to local failures, I combined everything And what I've done is that for each ground motion, I've assigned the global damage state that was coming from the two directions of motion, the higher between the two. And then if the same ground motion causes any collapse in both directions, and the consequent damage state is higher than the previous one, then it is override. And these are the results that includes everything. The conclusions are very similar to the one before. So the retrofit system is not affecting significantly the low damage state. And here you can see damage limit 1 and damage limit 2 curve, the green and the yellow. While if you focus on the DL3 curve and DL4 curve, you see that both of them were decreased significantly by the installation of the retrofit system. In particular, what was DL4 for the bare condition is now DL3 for the retrofitted one. And again, for the considered hazard, the collapse of the retrofitted building is practically nullified. This ends my numerical part. And finally, I only want to provide a brief discussion on how to improve the sustainability of the system. Because ideally, a sustainable system is standardizable, is reversible, recyclable, and can be integrated with some energy retrofit system. Of course, we couldn't cover all the aspects for the shaking table test, so we found it important to review it, even a posteriori, because it still has to be put in the market. We realized that we use a non-dry connection to connect timber post and masonry, and this connection jeopardizes the reversibility and also the recyclability. So we found a way to substitute it, and we found also new screw connectors that weren't available at the time of the test, that are specifically designed to connect timber and masonry in a dry solution. So we checked if we could use it, and we wanted to evaluate the influence of such a small detail on the overall emission and cost, just considering the amount of material used. We ended up with 50% of steel saved, 80% of cost saving, and 4% of emission saving. And moreover, of course, the retrofit solution became totally reversible and recyclable. To conclude, the out-of-plane response has small influence for a low level of damage up to DL3, while it has significant influence on the attainment of DL4. And we found out that considering also local failure mechanism in both directions is suggested, because it can be important, but it's also true that in our case the building results more vulnerable in X direction. The retrofit system effectively prevents the onset of local out-of-plane mechanism and enhancing plane and out-of-plane capacity of masonry walls. And the impact of the proposed intervention is increasing with increasing of damage. Finally, the sustainability of the retrofit can be improved by using dry connection. Moving to further researches, there are many that can be done. More experimental investigation could decrease the uncertainties associated with the defining damage limits. Micromodeling approach could consider simultaneously global and local failure mechanism, can consider other sources of variability, and can validate the work you presented today. The application of the retrofit system to other masonry topologies is also very interesting, because our system is fundamentally modular. You can change the size of vertical timber posts, the size of tie downs, the size of OSBs, the size of nails. You can change everything, so you can adapt to your needs. And out-of-plane dynamic tests on retrofitted piers are needed, because, as I said, we calibrated the out-of-plane response of retrofitted element based on a static test. And yeah, well, the sustainability part can be widely extended. My original idea was more rigid, but yeah, you can combine it with energy retrofit. You can perform some studies as the one proposed by my colleague Martina Caruso, which was my very first idea, but then I couldn't, of course, make it. And then perform a life cycle assessment on the intervention and compare it with other, integrated with other retrofit system and see the optimal solution. So this ends my presentation. Thank you for the attention.
Thank you, Marco. Questions by the committee, starting with Professor Giongo.
First of all, I want to congratulate you for the nice presentation, very extensive, very detailed, and also for the work itself, but a really extensive experimental part, and I believe it will have a remarkable impact both on academia and also on the practitioner. And so I also have had the pleasure to read your thesis, so the most relevant question that I had I already made. So right now I only have some minor ones, and the first one concerns the connection.
Yes.
You selected that also as part of your preliminary evaluation of the environmental impacts of the retrofit itself. Mm-hmm. And so were you able to isolate the contribution of the connection from the experimental result and numerical results in order to anticipate whether it'll have an impact to replace some adhesive connection with dry connections? And yeah, that's the first question.
Okay. Thanks for the question, first of all. Actually, no, we couldn't go deep in the forces that were taken by the connection. But we also see that in all experimental tests, the connection between timber and masonry didn't suffer any damage. All the other damage was outside that connection. It's also true that we were working with the calcium silicate masonry. Calcium silicate masonry was discovered to be very fragile. So the masonry itself is very fragile. And maybe it could be also had an impact on the non-damaging of the connections. But again, the use of the dry connection should be definitely tested, especially with our type of masonry.
So, because the follow-up question was, in your finite element modeling, how did you consider the connection and its stiffness? So I assume you assume it as rigid.
Of the connection. No, we basically consider them splitting the masonry elements for displacement compatibility between the vertical truss and the masonry. But we didn't model exactly the connection, also because we were using macro element model. So already splitting the masonry was already giving a high computational cost to the program.
Okay, and so just the truss element, so it has axial stiffness and strength and also bending, or just axial?
Only axial.
Okay.
And we modeled the ending part to return the force displacement relationship of the tie downs, while the middle part is just property of the timber element. So it's supposed to concentrate everything on the tie down element.
And I also have a minor question regarding the setup of the retrofit. What's the need of the sill element, timber sill element at the base? Why not just connecting the post directly to whatever foundation you have with the tie down?
We have two reasons, I would say. The first one, in the component test, we wanted also, I can show you the picture, maybe if it's not. Anyway, in the first experimental test, we wanted also to prevent sliding, so we provide some additional anchors. While, okay, here you can see. Yeah, I couldn't mention, but you see here there are some additional anchors. Do you see the? No, you don't see.
Yes.
There are some additional anchors on the top and the bottom because we want to prevent sliding. And but from the improvement of overall connection point of view, we use them to clamp the system, to the RC slab. You see here, this is the section of the top steel plate of the ground floor, and this is the, do you see that? Anyway, and we used them also to improve the connection with the timber floor system, because we used the angle to connect the vertical post to the top steel plates, and then we nailed the top steel plate to the spreader beam every 10-15 centimeters, I think.
Okay.
So it provides also an additional connection to the floor system.
So I have two more questions, if I may, very quick. So the first one is that I understand that you decided not to apply the plywood or the OSB panels to the north side and south wall because they were long and strong, but then you discovered some torsional movement that engaged the strength. So what do you expect it would have been the impact if you had applied the OSB? Given that also, I assume, and that's another question that I have, in your modeling, in the modeling of the retrofitted building, did you assume that you have also the shearing on the north and south wall, or no?
No. We modeled the OSB only longitudinal sides and not in the transversal side. So I have to say that, first of all, if we put the OSB also in the transversal side, we couldn't have seen anything during the experimental test because it would cover the masonry. Or because we already had all the longitudinal side totally covered, and so in this way we could also observe the response of that was. In real application, I think it would be kind of an owner choice because I mean, if you need it maybe for non-structural systems, if you need the cavity of the wall, let's say, you can put the OSB even if it's not necessary because it's only 18 millimeters thick, so it's very thin. From the invasiveness point of view, putting a strong back or a vertical post or an OSB more or less is the same. But and it's also true that in reality we don't know that the ground motion is coming to one side. So would be case dependent, I would say.
Okay, and how did the shearing to framing connection fare?
Sorry?
The connection, the nails, I guess, between the OSB sheets and the framing performed? Yes. Because if, I don't know, I expect them to exceed the yield condition, but if they didn't, then you might have applied plywood north-south and then remove it after test and go back, something like that.
That's also.
Other questions from the committee? Other questions from the committee?
Congratulations for the presentation, very clear. And I have a brief question. You suggested that this kind of intervention is possible to be applied also to other kind of masonry. Okay. You thought about a design methodology for this or not?
Yes. One of the best things actually about this retrofit system is that actually you can easily compute the contribution, the flexural contribution and the shear contribution, because the flexural contribution is just a matter of the tie down you put. So you can compute it based on producer values, and you get the proper modeling of the retrofit system. And the same goes for the OSB sheeting, because everything is suggested by the American Wood Council. They have formulation and everything mainly based on the type of nail, because the OSB works as function of the nail resistance, basically. So they suggest us, based on what we want to add to the masonry, they suggest us the nailing, the thickness of the panels, and everything. So you can very easily decide the contribution that you want to add and just add it to your building.
Thanks.
Any questions from the audience? Yes. Okay. Don't think so. So I will thank you once again, Marco.
Thank you.